In this lecture, we discuss about results of thin airfoil theory when applied to symmetric and cambered airfoil. Further, we discuss about the dependence on airfoil shape, how it affects flow separation and stall when we consider real viscous flows, and we will introduce a discussion on high lift devices. So, last time we had derived the equation for thin airfoil theory, and then let us now try to apply this equation to symmetric and cambered airfoils. So, for symmetric airfoil, the camber is 0, that means z is equal to 0, and therefore, this term goes out from the equation altogether, which basically means you just have the effect of angle of attack on the right hand side of the equation. Now, it comes down to working out gamma xi. Xi is a dummy parameter, and we substitute a function in order to bring about a transformation. That means, we are going to obtain the solution of gamma xi in a transformed plane, basically the theta plane. A specific location along the chord will be identified as x, like we showed in the previous diagram. So, you may recall that x was a specific location on the chord, and for that the corresponding value of theta is a specific value theta naught, while theta is for a general location. So, if you apply this transformation, the limits of integration gets changed to 0 to pi instead of 0 to c. Gamma xi basically becomes gamma theta sin theta d theta by cos theta minus cos theta naught. This is how the expression looks now, and on the other side, of course, it will be u infinity alpha. Now, there is a bit of trigonometry, application of identities, etc., by means of which the solution is obtained. We are not going into the details of the solution, but we are going to the final result, which says that the gamma theta happens to be this. This is the final distribution of gamma, and incidentally, it also satisfies the condition that gamma trailing edge, that means x equal to c corresponds to theta equal to pi, is also equal to 0, and this would come by application of the L'Hopital's rule, because you will have an indeterminate form like this when you apply this gamma distribution. So, in that case, with L'Hopital's rule you will be able to obtain it. Once you have got gamma, you can now integrate that. So, that is the basic definition, but in the theta plane it will be in this form, and once you do that, it will turn out to be so. These derivations, we are doing it in a very concise way. You are encouraged to explore this derivation, which you will find in many of the references that I have provided. Now, once you have found gamma, you put it into the Kutta-Joukowski's theorem, and then the lift comes out to be pi alpha c rho infinity u infinity square, from where you can go to the lift coefficient. So, what will be the denominator, this is your dynamic pressure times C into 1. So, 1 is for unit span, that gives you the planform area. So, this is the planform area S basically. Once you do that, you will find this is 2 pi alpha, which means that dCl d alpha is equal to 2 pi. So, you have now got the lift curve slope. So, 2 pi per radian or 0.11 per degree change in alpha. That is how we interpret it. How about pitching moment? Let us try to work it out about the leading edge. So, this is your airfoil, which basically has become a flat plate now because there is no camber. If you go a distance xi, you come up with that element d xi, and with the elemental vorticity it produces a dl, and there is gamma, an elemental gamma given by the strength of the vortex sheet times the d xi. So, in order to get the moment about the leading edge, you have to integrate the entire distribution. So, xi dl, all such contributions have to be integrated, and understanding that this is rho infinity u infinity times d gamma, you will find that the result comes out to be q infinity c square pi alpha by 2. This is the dynamic pressure. So, this is the expression for the moment about the leading edge. If you obtain the coefficient, it will turn out to be pi alpha by 2, which incidentally is equal to CL by 4, because you already know the expression for CL. Again, earlier we had shown equivalent moment systems, where we had expressed Cm leading edge equal to minus CL by 4 plus CMC by 4. But incidentally, Cm leading edge is equal to minus CL by 4. So, these two terms cancel out, giving you Cm C by 4 equal to 0. That means, for symmetric airfoil, the Cm at quarter chord is equal to 0, which means on one hand it is the center of pressure because the moment is 0. It also means that the aerodynamic center is at quarter chord, because it will remain 0 irrespective of alpha, because we have taken a general alpha and it is found to be constant with alpha. Therefore, the quarter chord location happens to be both center of pressure as well as aerodynamic center of a symmetric airfoil. So, these are very, very important findings which you have to keep in mind. What about comparing these results which are coming from a potential flow theory with experimental data which is coming from the real world? This is your potential flow theory result, that CL is equal to 2 pi alpha. We are drawing it as a straight line. This is your Cm C by 4 equal to 0 result, which is also coming from potential flow theory. And now, let us superimpose some of the experimental data. You will find that the experimental data taken for one of the symmetric airfoils is not far from it in the low to moderate angle of attack ranges, both on the positive and negative sides. What is the airfoil we are looking at? It is a symmetric airfoil, NACA 0.012, and the Reynolds number is around 3 million. So, almost overlapping with potential flow theory. What about the moment data? Moment data is also fairly consistent at the lower angles of attack, and of course, around stall it droops out. What are these angles like? These are typically of the order of about 12, 13 degrees or maybe 14 degrees at which the stall onset of stall is taking place. So, we have essentially an excellent match between potential flow theory results and experimental data at low, moderate alpha below stall. That is a huge encouragement for us. How about a cambered airfoil? You remember that the dz dx remains in the case of cambered airfoil, and when that happens the solution is ought to be a little more complicated. So, we will again provide the solution directly over here without any formal proof, but many of the books which we are referring would have a detailed proof, and you are encouraged to study that in spare time. So, this would be a solution for gamma theta, and there are coefficients that we see over here a naught, a n, etcetera, and in principle there are an infinite number of terms in this series. So, what do those terms look like? A naught is given by, you notice that it is dependent on the shape of the camber line. So, dz dx basically depends on the camber line shape. So, if you are provided this function, you can always calculate what this is, and therefore, you can find out this coefficient and substitute it in that expression to give gamma theta. In addition to the a n's, you will find that the a n's are also dependent on dz dx. So, you remember that a specific location x is dependent on this angle theta naught. So, that is what figures over here. And the final result which comes out by integrating that gamma along the entire length of the chord comes out to be like this, where only two of the coefficients are necessary to be substituted. And by Kutta-Joukowski's theorem, you can obtain the lift per unit span. And what does that come out to be? It comes out to be again a function dependent on the first two coefficients, from which you can non-dimensionalize and express it in this form. Now, very interestingly, you will find that when you take a derivative of this with respect to alpha, you get back the 2 pi. That means, the slope of a cambered airfoil is the same as that of a symmetric airfoil. Slopes remain the same. What changes? The zero lift angle of attack, that becomes negative for a cambered airfoil. So, what is that for a symmetric airfoil? It is 0. We recall from an earlier lecture that it is 0, but in the case of a cambered airfoil, it is going to be non-zero. Similarly, you will find that other parameters like Cm leading edge, Cm quarter chord, they can all be derived from this theory, and every time only the first two coefficients or first three coefficients will help us to work all these parameters out. So, last time For a symmetric airfoil, we found xCp to be c by 4, but this time you see it is shifting away from c by 4 because you have additional terms here. So, finally, what we find is that the thin airfoil theory can be extended to both symmetric and cambered airfoils, and we can find out all the relevant aerodynamic parameters of interest. So, now let us spend a little bit of time on the shapes of airfoils and how their real world behavior is affected by the thickness. So, we are going to discuss about the thickness effect on the stall behavior of these airfoils. So, all this time we were talking about the potential theory, where we were ignoring the viscous effects, but now we are going to look at the real world case where viscous effects are going to dominate. So, when experiments are conducted in low speed wind tunnels and lift and moment data for airfoils obtained from the theoretical results, that means the potential theory results compare very well. They do compare very well at low angles of attack, where the flow is basically attached and the viscous effects are confined to a thin boundary layer. But as stall angle is approached, we see flow separation takes over, and then the flow separation phenomena is much beyond the inviscid theory, and therefore, inviscid theory cannot predict it. We saw that the CL curve extends perpetually to large angles of attack remaining linear, which means it misses out the stall phenomena altogether. So, that is where we have to look at actual experimental data to see the viscous effects having an impact on the aerodynamic response. So, there could be thickness variation in airfoils, and we need to look at the effect on stall behavior. We will broadly look at 3 different types of stalls. The first one is called leading edge stall, and they are seen in thin airfoils, where maximum thickness is typically up to say 16% or so. You could have thinner airfoils than 10% max thickness, but the upper limit is around 16%. So, in such airfoils we see leading edge stall, where the flow separation takes place quite abruptly, and that happens of course on the top surface of the airfoil, which is facing the adverse pressure gradient, and origin of that separation is the leading edge of the airfoil. And then what happens is that the lift curve drops sharply in the neighborhood of the maximum CL, and leading to rapid decrease in CL beyond the stall. So, this is quite a dramatic stall phenomena, which is called as leading edge stall, because it initiates from the leading edge. On the contrary, for thicker airfoils, that means with thicknesses beyond 16% and much more beyond that, we have a different type of stall, which is called trailing edge stall, which means it is initiated at the trailing edge, and then it progressively and gradually moves upstream from the trailing edge towards the leading edge as the angle of attack is increased. But the CL alpha curve, when it goes into the stall, is much more moderately curved. That means, there is no dramatic drop in lift beyond stall. So, that is what is called as trailing edge stall. And then there is another kind of stall, which is called thin airfoil stall, that is with respect to sections which are much thinner than these, typically 1 to 3% thin, which is extremely thin really. You can consider say a thin flat plate, and that would be a typical thin airfoil stall. So, what happens is, near the tip of such a sharp airfoil, there is a sharp convex corner, and the leading edge of the airfoil produces a very rapid acceleration of the flow, and viscous flow is unable to remain attached under such a situation. So, there is a flow separation and formation of a recirculation zone. The flow generally reattaches on the leeward surface, creating a recirculation pocket or a bubble. So, we have a so called separation bubble at the lower angles of attack, but as the angle of attack increases beyond a certain point, it is unable to reattach at all, and the lift curve gradually bends over as alpha is increased, but it is at a much lower level of CL max corresponding to or in comparison with the trailing edge stall situation that we were talking about in thicker airfoils. So, let us look at some more features of these airfoils in the next few slides. So, this is a plot which gives you some more information in that direction. So, we have a flat plate which is the thin airfoil case, and it is going to encounter the thin airfoil kind of stall, and it is typically say 2% thick. You have a CL alpha curve where you can see that the CL max corresponding to the flat plate is really much smaller than the corresponding airfoils, and you find that a thinner cambered airfoil typically with say about 10% maximum thickness has a CL max which is larger than the CL max for a trailing edge stall case, where we have used the same maximum camber in both the cases. That means, the basic camber line for these two airfoils is identical, only thing is they differ in maximum thickness. So, what do we see? That first of all, the lifting surface, if you compare between the flat plate and the airfoils, there is a thickness difference. Even the thinner of the airfoils is much thicker than the flat plate, which basically means that thickness does have a role to play on CL max. And then beyond that, once you go into the slightly higher thickness ranges, over there on the lower end you have the leading edge stall, which leads to a dramatic post stall behavior. But if it is a thicker airfoil, then you have a much more gradual stall or a soft stall, as they say. Moreover, because they are cambered, the zero lift angle of attack is negative. So, you would have to go to the negative side of alpha in order to get the zero lift condition. So, let us try to look at the main points here. The airfoils shown in the adjacent figure have identical camber, but unequal maximum thickness. There is a sharp sudden drop in lift for the leading edge stall case, that is for the comparatively thinner airfoil. The trailing edge stall yields a gradual dipping of the lift curve at maximum lift. This is referred to as a soft stall. Similar soft stall at lower angles of attack is observed for thin flat plate, but due to a different phenomena, that is the separation bubble formation. It is not due to the trailing edge stall. The value of CL max is higher for the thinner airfoil compared to the thicker airfoil. So, you would have noticed the difference between these two levels. Fine. And then let us go back to these points at the bottom. All the lifting surfaces show identical lift curve slope in the linear portion, which matches with the thin airfoil theory result. So, whether it is a symmetric or a cambered airfoil, the lift curve slope theoretically is 2 pi. Zero lift angle of attack for the airfoils is negative due to positive camber, and 0 for the flat plate because it has 0 camber. It is a symmetric section. Thickness augments the lift generation capability of a lifting surface. This is clear from the difference in CL max between flat plate and the airfoils. So, we have some very interesting findings over here based on the difference in the thickness. We also got to see the effect of camber once again through the difference in the zero lift angle of attack and the consequent offset of the lift curve. Let us go into high lift devices next, and we have a few sketches of typical high lift configurations. So, in the trailing part of the airfoil, you find that there is a control surface which has been deflected, which is called as a plane flap. So, these are basically trailing edge flaps which increase the effective camber of the airfoil section. As you can understand that when you have a deflected surface like that, the camber will look more like this. So, the original camber goes that way, but with the deflected surface the camber changes. Therefore, the whole lift curve shifts upward parallel to the lift curve for the undeflected flap position. That is the basic idea. You could do it by other means also, that here it is hinged, and in this case it is deployed further down. Of course, it is hinged, but with a different mechanism where it creates a slot between the fore section and the aft section of the airfoil. Aft section basically means the flap. So, there is a slot through which the flow can move. All right, you have other possibilities also. You have a double slotted flap configuration, and you have the upper diagram representing the configuration when the flap is in deflected position. So, you basically have two portions in the flap, and they are stored in the rear part of the section, and then they are deployed based on need. So, here they have been deployed and the flaps are deflected down. So, you can imagine that when you draw the camber line, it will look more like this of the entire lifting surface, and therefore, it is enhanced because of the deployment of the flap. When they are retracted, they get into the slot region, at least the smaller flap, and the larger flap forms the trailing edge of the section. So, in that case the camber line will move like this. Therefore, there is a clear augmentation of the camber in this case, which means that these kind of devices would generate higher lift. Let us now look at the aerodynamic response through the CL alpha curve. This is with the undeflected flap for a symmetric airfoil. And then we have two flap deflections. One is positive when it is deflected down. So, it is considered positive when it is going down, negative when it is moving up. It is hinged in a manner that it can move down as well as up. In that case, what you see is that when it moves down, the lift curve pushes up. When the flap is deflected up, the lift curve pushes down. So, this is due to the positive camber, while this is due to the negative camber. The shifting is taking place. The whole lift curve is moving up or down, keeping its slope unchanged. So, if you are looking at a particular angle of attack in an undeflected position, this is the CL that it is generating. In a deflected position, in the positive sense, there is an augmentation of the lift by so much. That is essentially the effect of the lift augmentation due to deflection of the flap. So, the CL max for a given airfoil varies with Reynolds number. The peak value is dependent on Reynolds number, whether it is deflected or not. Higher values of CL max are achieved at higher Reynolds numbers. That means, if you increase the Reynolds number compared to this case, you will see gradually the CL max point pushes up to a certain saturation level. The trailing edge flap is a portion of the trailing edge section of the airfoil that is hinged and can be deflected upward or downward. When the flap is deflected downward, that means it is a positive angle, the lift coefficient is increased, and it is due to the effective increase in the camber of the airfoil. Opposite happens when it is deflected upward. At a given angle of attack, the lift coefficient is increased by delta CL amount by the flap deflection. The value of CL max is increased by flap deflection. So, you see there is a increase in CL max. This is the increase. The angle of attack at which CL max occurs is slightly decreased when the flap is deflected. So, this is the reduction in the angle of attack corresponding to the stall between the undeflected and deflected cases. So, though CL max increases, the stall occurs at a slightly lower angle of attack. An effective airfoil produces a high value of CL max and simultaneously it produces low drag, so that its L by D ratio is high, which means its aerodynamic efficiency is high. For a complete airfoil, the maximum lift coefficient in capital CL max, remember, because it is a 3D body, determines the stalling speed of the aircraft, and that stalling speed is given by this expression. If the maximum lift coefficient of the airfoil that is deployed in the wing of the aircraft is increased, it can lower the stalling speed, because an increased CL max reduces V stall. That means, you can slow down the aircraft and bring it down to a lower speed before it stalls, or you can increase the payload weight at the same speed. That means, you can increase this W keeping the stall speed same. Further, it improves the maneuverability of the aircraft. For example, it can reduce the turn radius or it can increase the turn rate. So, such maneuverability advantages are also gained. High lift devices, when deployed at the trailing edge or leading edge in a combined manner, can augment the CL max of the airfoil section significantly. So, today we could discuss about the high lift devices deployed at the trailing edge in the form of trailing edge flaps. In the next lecture, we will take up the leading edge slats. So, in this lecture, we discussed further about thin airfoil theory and its application to symmetric and cambered airfoils. Subsequently, we looked at how thickness distribution on an airfoil can influence the stall behavior of an airfoil, and then we came into the high lift devices and we discussed about the trailing edge flap and their effect on the CL alpha curve. Thank you.